Hi, everybody. We seem to be getting smaller and smaller. Is it an indication on my teaching? Or?
This is more about the people.
So at least we have a video, so tell the other students that I'll try to upload the video as soon as possible. And say they should watch it. Next week we have the second quiz, which will be about one-way ANOVA. This lesson today, planned comparison, and next week's post-hoc test. So today we're starting with fresh new material, something that you haven't heard last year. So week 5, about time.
Sorry, only one way ANOVA.
The quiz one-way ANOVA, planned comparison, and post-hoc test, which will be next week. So again, three lessons to revise. So today we're going to talk about planned comparisons, but more specifically and more interestingly, we're going to talk about Game of Thrones. Who haven't watched at all, doesn't know Game of Thrones at all? Doesn't know what it's about at all? Okay. So at least most of you will be with me, but those of you who haven't seen it, the basic premise, we can say that we have different noble houses, and they all fight against each other to see who will be king of the seven kingdoms or queen of the seven kingdoms. And so that's what basically it's all about, different royal houses fighting one against another and the personal stories behind it. So the original thought that I had for today was to see like a comparison between whose house is prettiest, because all the actors and actresses are really beautiful. But then I decided to start to go in a different direction. And this is today's story. So, the maesters, these are maesters of Westeros, wanted to examine which noble house will have the upper hand when war breaks out. They sampled 20 warriors from each of 5 houses and rated their fighting skills from 1 to 20. So we have these 5 houses that we focused on for today. So it doesn't really matter the names, but Tyrells, Lannisters, Baratheons, Stark, and Targaryens. Okay? So, is the design clear? We have 100 warriors from 5 different houses, right? So we can't compare them obviously with just one t-test. Right? We have 5 groups. It's all between subjects. We have 20 different fighters from each house. So let's look at the results they found. Okay? So these are the results. We have x bar 1 to 5. Each one of these are the averages. Okay? So we see there are some descriptive differences between the different houses, right? So we can calculate SSB. SSB, I remind you, sum of squares between the groups, right? And we get 800. You can try it at home and get 800. Then we can calculate MSB, the mean sum of squares between, and we'll get 200. Let's say that SSW is this number, right? 2,375. Why is it this number? Just because I invented it. And we get that MSW is 25. Okay? If we know MSB and MSW, variance between the groups, variance within the groups, we can calculate F, right? F, we're asking, can the variance between the groups overcome the variance within the groups? Or is the obtained difference larger than the difference we expect by chance? So we get F equals 8, and then we can compare it to the critical F. So this is the critical F with 4 degrees of freedom between, right? Because we have k minus 1, and 95 degrees of freedom within n minus k. I want to write these down so we have a note for them later. So this is the overall ANOVA. Okay, or another name for the overall ANOVA. This is something that's going to pop out once in a while, so you'll know what it means. This is also the omnibus ANOVA. Omnibus basically just saying overall, the general ANOVA. Okay? So you might see this word, the omnibus ANOVA. So let's write down that we have DFB equals 4, right? And DFW equals 95. And also I write down that SSB equals 800, MSB equals 200, SSW equals this number, 2375, MSW equals 2000. Okay, so I wrote it down for future reference. So we can see because F, the obtained F, was larger than the critical F, we can say the result is significant, right? The obtained difference is significantly larger than the difference expected by chance. But what is the conclusion we can get to? H0 says that all the different houses have the same fighting scale. There's no difference. We rejected H0, so we can say, okay, there's some difference. What's the difference? What is the difference? Right? H1 won't tell us what is the specific difference. Right? So the Meisters can conclude that there is a difference between the groups in the population, i.e. not all the groups have equal fighting. But that's not a good enough conclusion for us. Right? You wouldn't do a drug test with 5 different drugs and have the conclusion, yes, there is some difference between the drugs. Right? You want to know which one is significantly better or worse than the other. And we have some hunches, but we can't know for sure. Can we say that the Targaryens are better than the Starks? Can we say that the Starks are better than the Lannisters? We don't really know, right? We have to do further testing in order to know. So that's why we're going to go into these 2 lessons, plan comparisons today, and post-hoc next week. To answer this question, when the ANOVA is not enough, we have to ask further questions. Okay, any questions so far?
What is the overall ANOVA?
So the overall ANOVA is this?
This?
Right.
Never. This?
Comparing all the groups one to another, we call it the overall ANOVA.
Yeah.
Yeah.
Oh,
But
yeah.
you're going to see them going to have different Fs now. Each specific test will yield a different F. So this is the F
These
from
are
the
ANOVA.
overall ANOVA, or the omnibus ANOVA.
Okay, that's what I wanted to know. Word underneath.
Yeah.
Could you theoretically run a bunch of t-tests?
That's a very good question. I think I told you that a great question is a question I can answer in the next slide. So that's a great question. So this is one Meister says, let's just conduct multiple t-tests and compare all the different groups. But Lewin, which is the good guy, that's not a good solution actually. Why is it not a good solution? It seems so intuitive. So just a sec. So the reason is that the more comparisons we conduct, the more likely that at least one comparison will be significant due to type 1 ill. Now that's not intuitive enough. So let's remember the example with the hat. Okay, we have a hat, right? A red hat that contains 99 red balls and 1 blue ball. We have 100 researchers, each taking 1 ball, looking at it, and then returning it back to the hat. Okay? Looking at it, oh, it's a red hat. It's a red hat. It's a red hat. Oh, it's a blue hat, right? So after 100 times, it's almost certain, it's not certain really, but it's almost certain that at least one of them will be wrong and conduct type 1 ill. Okay? So the more comparisons we conduct, the more likely we'll conduct at least one type 1 ill if H0 is correct. Okay? I'll give you a story. A doctor in a mental institution talked with my advisor, Okay? And he said, I gave my patients a battery of different tests. And I found a significant difference between schizophrenics and non-schizophrenics on one of the tests. And I think this is an important finding and we should publish it. And she said, well, did you search for this difference or did you just find it by just one of the findings? No, I just found it from one of the findings. So it makes it less certain that it's a real effect because if you throw your net wide enough, eventually at least one of the tests will be significant just by chance. Okay? So we will not conduct multiple t-tests. We have different solutions. Is this intuition clear? That's very good. it's not an easy concept to grasp, but it's very good. Gosh.
In that story, are we assuming that somehow the tests are dependent on one another? Or not at all?
No, independent. But still, right with the red hat. Independent completely, they return the balls. Eventually one of them will get the blue ball. Eventually. So we're calling this type 1 error across multiple across multiple comparisons. We're calling it the family-wise alpha. Okay? Not the alpha in one comparison, but an alpha in what we call a family of comparisons, or a set of comparisons, yes.
But if they're all independent, then don't we have that exact same probability every time we run a test?
But if you're looking at it from afar, you'll say, okay, what is the chance from 100 tests not to get the blue ball, right? And then you'll have, this is more combinatorics in first year, but basically intuition. In your intuition, you will say, okay, eventually one of them will get the blue ball. Okay, so again, the term is family-wise alpha. Okay, the chance of making type 1 error in a family of comparisons, or another word for it, in a set of comparisons. And this is what I said now. So the more comparisons we conduct, the larger the family-wise alpha. Now we can actually calculate exactly what is the family-wise alpha going to be. Oh, just a sec, just wanted to show you the image. It's rather slow, but look at these five groups, okay? If I conduct all these t-tests, how many t-tests will I conduct? So I have 5 plus 4 plus 3 plus, it's 4 plus 3 plus 2 plus 1. Okay? So overall, from these 5 groups, I have 10 paired comparisons. Why am I calling it paired? Because each time it's one pair, right? Comparing group A to group B, group A to group C. So with these 10 comparisons, I can calculate what is going to be my family-wise alpha by using this formula. Okay, you have this formula in the formula sheet. The formula is 1 minus 1 minus alpha. Okay, so alpha is usually 5%. Right? In the power of C. C is the number of comparisons. So we get 1 minus 0.95 in the power of 10. And we get 0.4. This means that if H0 is true in all of these comparisons, we have 40% of making at least one type 1 error. Right? And keep taking balls from the hat. Eventually, one of them will be wrong. Okay? So from all these comparisons, if in the population there's no difference, eventually I find one significant difference, which is significant just by chance. Yes? C is the number of comparisons. Okay, so here we have 10 paired comparisons, so we do in the power of 10. Yes?
Family-wise alpha can never equal 1. Is that
No, never equal.
why is that in the formula? Because
We're always 1 unless you use an alpha of 1. Of 10, 100%. That's the only case where it can be absolutely 1. Okay, so that's bad. Okay, I told you in I think the second lesson, that type 1 error is called type 1 for a reason. It's a very serious error to make. Yeah.
But if we reset, if we lower the alpha for 0.0.
That's a very good intuition. That's what we're going to do next week. Okay, very good intuition.
But still, if you have a lot of groups, then it will keep adding up.
Yeah.
And even lowering it only helps to an extent.
Yeah.
To an extent, right? That's good intuitions. Keep it for the next few slides. Okay, for a few slides, and then we'll talk about it. Yes.
But if you lower the alpha too much, then you can't really get a significant result, so you can never reject.
Good, good. You're having very good intuitions about it. Very good. Okay, I'll continue though, and then we'll come back to it. Okay.
Right.
Okay, so I told you type 1L is very bad. Okay? The doctor talked with my advisor, right? If that result was a type 1L, and he would publish it, and then would go forward with it, and then they will start a new treatment based on it, that's very bad if it's a type 1L. Okay, so we don't want to make even one type 1L. Okay, not even one. So we have to find a way to reduce this family-wise alpha. We want a family-wise alpha that's reasonable. What's reasonable? 5%. We want the smallest family-wise alpha that we can manage. So this is called, this increase in family-wise alpha, it's called alpha inflation. Okay, that's the phenomenon. The more comparisons, the more alpha is inflated. Yes?
Okay, yeah, so the more, so when we have ANOVA, we try to have like the smallest alpha.
Right, if we have, what would happen if we only had one comparison? C would equal to 1, right? And then 1 minus 95 in the power of 1 is 5. We get alpha of 5. So if we had just one comparison, we remain with just 5%. Okay. The more comparisons, the larger the alpha. Yeah.
We'll have a larger chance of finding the result, but it won't tell us exactly where the result from the ANOVA came from. It will tell us where it came from, though, right?
If you do all of these, yes, you will find some difference, but you don't know if this difference is based on type 1 or not. That's
Right,
the problem.
but we got a significant result with the F test already.
Yes.
So we already know that there was some difference. Now we're just identifying where it is. Who cares how?
Right, right, but still, you might find within this family of groups.
A few differences that we
Yeah.
that didn't contribute to the
Yeah.
ANOVA.
Okay, so there are two methods. Two methods, two lessons. The first is plan comparisons. Plan comparisons are a limited number of comparisons that follow strict rules. Only under these strict rules we are allowed to do these extra few comparisons without risking alpha inflation. Okay. The second method, exactly what you said, post hoc tests, which are multiple comparisons, where we change the alpha, and then we have much less power. Okay, but you don't have to remember that. We just have to take this into consideration into next week. Okay. Now, if I tell you that the second method has less power, okay, this means that in the most cases, we'll prefer to use the first method. Right? If the second method has less power, then the first method has more power. And we love to have more power. In plan comparisons, we can test few comparisons without risking family-wise alpha inflation. And we have critical conditions. Only under these conditions, we're allowed to conduct plan comparisons. First of all, they have to be planned, okay? And that's more of an ethical norm than a statistical norm, okay? Because if you know in advance what you're looking for, it's not exploratory. It's not like you're fishing for something, okay? You're looking for something very specific. A lot of the times, because you're looking for something very specific, you'll also have one-tailed hypotheses. Not always, but sometimes you'll also have one-tailed hypotheses because you know what you're looking for. 2. The comparisons also have to be independent from one another. There's an ugly word here, orthogonal to one another. Okay? Orthogonal. So the comparisons have to be independent. Now, of course, that doesn't mean a lot right now. A lot of this lesson will be about understanding this sentence. What does it mean to have independent comparisons? Okay, so don't worry if you don't understand it right now. So these are the critical conditions. I think that's it. Yeah.
What does it mean by plan?
So you have to know in advance what you're looking for.
What are the conditions that will, what are the variables that will produce the amount of difference or specific difference or what?
If you're looking for, let's say you have three groups, and you have 2 drug groups, and 1 control group. And you know in advance that you're planning to compare both drug groups to the control group, and you want to compare each drug to one another. Okay. These comparisons are planned in advance. You're not going into a large data pool and then saying, oh, let's just check this and just check that and check this, right? And it's not like that you're looking at the data that you found and then decide what comparisons you want to make.
You're saying we're not, when you say we need to know what we're looking for, you're not talking about a specific result, you're talking about what we're comparing it to.
Yeah, we're comparing specific groups. Now, the idea is that a lot of times we do something else. We look into a large data pool, we look at the averages, and then we decide what we want to do. That's not planned in advance. Okay? That's just conducting good research after we already got the results. Okay? But planned in advance, it means that it has some theoretical significance, right? You know from the theory what you're looking for. Okay. So, let's continue. So, independent versus dependent comparisons. I'm going to start with appealing to your intuitions, and then I'll show you the formal way of defining dependence versus independence. Okay. Dependency means that the result of one comparison is informative to another comparison. That is, knowing the result of one comparison will give me some information, not all the information, but some information about another comparison. Okay. So let's see cases of comparisons. So let's say comparison 1 is Tyrrell's versus Bannister's. Okay. 2 houses fighting against another. Who has the better fighters? Comparison 2 is Baratheon versus Starks. If I know that the Lannisters won in comparison 1, does it tell me anything about who will win in comparison 2? No, of course not. Different groups altogether. So this case is that comparison 1 is independent from comparison 2. Completely independent, doesn't give me any information. Right? Here's a more complicated case. We have, again, Tyrell versus Lannister. This is comparison 1. And the second time, we have something else. Now what? Okay, sorry. All the verses is missing. You'll understand. So Tyrell versus Lannister. In this case, we have something different. We have this plus. This plus will tell us that in this case, the Tyrell and Lannisters are together fighting against the Starks. So, an alliance of Tyrells and Lannisters, right, as we see from the show, against the Starks. Now, if I know that the Lannisters are better than the Tyrells, does it tell me if their alliance together is better than the Starks?
No, you don't know anything about the Starks.
Right, we don't know anything about the Starks. Is this idea clear here? Right? Knowing that the Lannisters can beat the Tyrells will not inform us if the Starks can beat both. Maybe the Starks are pretty good. Maybe the Starks are pretty bad. We don't know. Okay. So in both cases, we have independent comparisons, completely non-informative. Okay, so this is the case of independent comparisons. Any questions so far? Good, good. Bring you with me. That's good. Now let's see a case of dependency. So, if I'm comparing Targaryens to Lannisters, and the second comparison is Targaryens versus Tyrell and Lannisters. Let's say I know that the Targaryens won versus the Lannisters. Okay. Does that inform me about this comparison? Yes, right? Because the Lannisters are part of this comparison. Right? So now I know they already won half of the alliance. Now, I don't know, maybe the Tyrells are really, really strong, okay? Maybe it won't be a significant difference here. But it still gives me some information that I can take into account when I'm conducting this comparison. So what I'm saying is that comparison 1 is dependent on comparison 2. Because knowing that the Targaryens can beat the Lannisters will give us some clue, again, not all the information, but some clue, as to whether they can beat both Lannisters and the Tyrells. Not certain, but informative. I feel that the microphone keeps getting turned on and off. You can hear me without it as well, right? Okay. Okay, so this is a case for dependency. Okay? Is it clear why these comparisons are dependent? Good. Good. I think we're all on the same page. That's good. Now, I want to show you a method of how to choose orthogonal comparisons. Right? We have these 4 groups, and we want to choose orthogonal comparisons. By the way, I forgot to say something. This comparison, right? This is not a paired comparison. Right? Because it's not just group A versus group B. This is Targaryens versus a combination of 2 groups. So now we're going to call these kind of comparisons complex comparisons. Okay? They're not paired or, in other words, simple comparisons. These are complex comparisons because you have to use a combination of several groups. Okay? But still, even though we have just these 3 groups, eventually we have 2 sides, right? On one side, the Targaryens. On the other side, this alliance of Tyrell and Lannisters. Okay, so these are complex comparisons. Now, if the first comparison is Tyrell versus Lannister, and the second comparison is Baratheon versus Stark. Okay? We said before, obviously these are independent. Now we want the third comparison to be independent from both the previous comparisons. We want the entire set of comparisons to be independent of one another. So how do we choose how do we know what's an orthogonal comparison? So I want to call this a game of alliances. Whenever 2 or more groups fight one against another, right? It works well with Game of Thrones. Obviously, when you're comparing different drugs, they don't fight one against another. They have to conjoin for the next battles, right? For the next comparisons. They participate in. Once the Tyrells fought the Lannisters, they can't fight alone anymore. All the next fights have to be with the Lannisters in an allegiance. So I have to do an alliance between these 2. But I also have to do an alliance between these 2, right? So what do you think is going to be the next comparison? We're going to have the Tyrells and the Lannisters versus Baratheon and the Starks. Okay? And if you think about it, knowing that Baratheon Stark allegiance can win against the Tyrells and Lannisters doesn't tell you anything about this comparison. And this won't tell you anything about this comparison. So that's independent. But now, this alliance fought against this alliance. So now, they have to go into alliance. So all four of them will have to go to an alliance against Targaryens. So whenever we have a comparison between two groups, a fight between two houses, from now on, these have to come together. Okay? They have to come together. There's no possibility, and I'll show you in 2 more slides why not. Now let's look at it from the other way. First of all, is this idea, again, I'm appealing to your intuition still. Okay? This is not the formal method of checking for orthogonality.
But there's other, I mean,
Other,
I get what you're doing, there's other combinations. that
right,
can-
there are other combinations, absolutely.
So why do we have to suddenly combine? Why not go through all the combinations and then combine them?
So again, we said that the rule here for plan comparisons is that they have to be orthogonal.
Okay.
I'll tell you.
Well, but there's other orthogonal.
Right, and that depends on what you want to ask, right? You're planning the comparisons, but you have to plan an orthogonal set if you want to use plan comparisons. Another option. So let's say Tyrells and Lannisters versus the Baratheons. Okay. So now we know that these two houses fought against the Baratheons, so now they have to come in alliance, right? So let's say the next comparison is all 3 houses against an alliance of Starks and Targaryens. Yeah, turn off. Yeah, that's annoying. Okay. Next time I'll try to fix it. Okay, so we have an alliance here and an alliance here. But in the previous slide, we built it from bottom to up, right? Each time we got a larger alliance and a larger alliance. But now, all the alliances are made. So what happens now? Now the alliances will break down. Okay, so if the Starks were in alliance with the Targaryens, in orthogonal comparison, okay, whenever 2 or more groups form an alliance, they have to fight one against another. So Starks have to fight. It doesn't mean they have to fight, but that will be an orthogonal comparison. Okay? And the Tyrells will have to fight one against another.
Why do they need to fight in order to make an
So they don't have to fight. Maybe the word they have to seems a bit too strong. So again, we're talking about what is the next orthogonal comparison, right? So if you have an alliance, the next orthogonal comparison will be to break up the alliance.
Afterwards, yeah.
Okay? Once you've chosen comparison 1 and comparison 2, now you're thinking about, okay, what next? What else can I compare? So you can compare breaking up the alliance. Okay, so this is the game. You're forming an alliance, you're breaking down the alliance. Yes.
Isn't there more at stake though for making an error in this? Because if you make an error with one of the comparisons, then it like leads into all the rest of them.
But that's the thing. Because they're independent, it doesn't lead to the rest of them. That's exactly the point, right? If I made a type 1 arrow here, it will not affect my chances of making type 1 arrow here. Right?
Why? Like if you're, for example, when you're just comparing 2 groups, right?
Yeah.
So you're looking to see, okay, this group is obviously stronger than the other group.
Yeah.
So then I know that that's the winner, and then I combine them together. So I know that, like, for example, the Lannisters are stronger than the Tyrells, and now they're a group. Now I'm comparing them to another group. So,
Yeah.
like, to see if that group is stronger than the other.
So let's say I got by chance just by sampling L, I found that the Lannisters are a bit stronger than they actually are, okay? And the Tyrells are a bit weaker than they actually are. So I made, just by mistake, this gap between them, which interpreted into significant comparison. Okay. Now, in their alliance, this result will nullify itself. The average of both houses will be the same average as in the H0 population. Okay? So these mistakes or these errors won't affect the next comparison using the alliance. So that's exactly the point. Because type 1 error in one comparison is independent from type 1 error in the other comparison, we get this situation where it's better, right? Yes?
How do you ultimately find who is the strongest out of this model?
You don't. Right. It's a good question. If these are my 4 comparisons, I can't find exactly who is the strongest. Okay? So we're not doing a Game of Thrones study trying to compare which is the strongest. Usually we're trying to find very specific, interesting questions. Okay? I'll give you an example. I did a study with 4 groups. Okay? I had 4 between subject groups. I had, how do I describe it shortly? Okay, so the study was that people read a description of a character and then they had to evaluate this character. Okay? Now I had a heterosexual character. Okay? I had a gay character. Okay? 2 groups. I had a bisexual character that was dating a man. Okay? And I had a bisexual character dating, what do you think? A woman, right? Okay. So I had these 4 groups. Okay? I did the ANOVA, found a significant difference. Now, I wasn't interested in all the possible comparisons. I was interested in 2 comparisons. I was interested in comparing bisexuals to not bisexuals. Okay? That was the first comparison that was interesting to me. I want to compare the heterosexual and the gay characters to the bisexual characters. Okay? The second comparison that was interesting to me is between the 2 bisexual characters. Okay? So you can see that, of course, comparison 2 here was independent from comparison 1, right? Because it's an alliance that we broke up. Okay? But all the other questions weren't interesting to me. I didn't care if this group had any difference from the heterosexuals in specific. Yes?
Couldn't you just done 2 t-tests with a significance level of 0.01?
That's a very good point. And next week, again, we'll see why we could do something very similar to what you're saying. Not exactly a t-test, but something very, very similar. Right, that's another way to do it. But what you
Because
said...
it's only like 2 comparisons that you're making. It's not like a multitude of comparisons.
Right. Still, it inflates the alpha.
Yeah, but if you do small alpha.
Then what would happen? You said it yourself. I have less power. Right? And this comparison, one of them at least, was with a p-value of 0.4, right? Just barely significant. So if I'd use half of the alpha, or alpha of 0.01, I would not get a significant result. Okay, so the point here is we can't find from this design who's best. Okay, that's not the point. The point is that we're going to ask very specific theoretical questions. Now, in this design, it doesn't really seem appropriate, right? We're just trying to find who's the strongest. But still, that's just to make the point that we can do something like this. Yes?
Yeah, I was just going to say that in the, it seems to me that in your example here, the bisexual group, the alliance, could be significantly different though than the other group, or vice versa, because of one of the groups within.
Could be, but then I'll see it in here. Right, it could be. It And I can ask more questions and I can make more tests to see if one or the other difference or not. But it's in both cases it's still two valid questions.
You're not inflating your alpha at all.
You know what? We'll talk about this later. For our purposes, no. There's no inflation in this case. Okay. One more question, then continue. Yes.
So what happens with the Baratheon group? Like the Tyrell Lannister, they combine alliances, but then they split apart. How about Baratheon? Because Baratheon, Lannister, and Tyrell did combine second time. So what occurs in the third stage with Baratheon?
So the third stage, we stopped asking the third stage. We stopped asking questions about the Baratheon. Look at this comparison. In this case, we used the Targaryens only once, right? We asked only one question about the Targaryens. So you were absolutely right. There are a lot of different combinations we can ask. It depends on what we're interested in.
Why would you even propose that in the beginning if that's really your original focus was between the bisexual and the bisexual? Why originally write that? I mean, at least start that in the process. Like, why even begin with that? Why form that group? Like, if your original
groups or these groups.
Those groups, the heterosexual and gay, that box. Why would you even form that if that was your focus?
What would have happened if I saw that there was a big difference? Like I still saw these are what I planned in advance, and happily for me, all the results fit in nicely with my hypotheses. But if I would see that, for example, only the heterosexual target is different from the rest, like in looking into the data myself, I would do auxiliary comparisons.
That's kind of still not so planned. Essentially, you set it up, then you're still working with the results you got. I mean,
no, I planned these are the comparisons of interest I had.
Mm-hmm. So you're saying that you were
the second.
Okay. That's all. The whole way you're actually going to do the two boxes of the bisexual. That was your whole plan comparison. But since you want to see, just in case there's a difference between a heterosexual and a bisexual.
I want a different hypothesis was that these two will be different from these two as well. One more question and then we continue. Yes.
So the first step is always going to be an F test and then comparisons, or if you know that
Great
that's what you
questions.
want.
Great questions. The last slide of this presentation will say that not necessarily. Okay? Great question. Okay, I'm continuing. So, let's formally define orthogonality. Okay? So far, there were intuitions, a game of alliances, appealing to your intuition about what's independent, but I can formally define what's orthogonal and what's not. Okay? We don't have to rely on our intuitions. So, we know that these comparisons are orthogonal, right? We said Tyrell versus Lannister, no information about Baratheon versus Stark. I can represent these comparisons with numbers. Okay? I can represent these comparisons with numbers. How can I represent them? So, for example, comparison number 1, I can represent Tyrell as 1 and Lannisters as -1. Why 1 and -1? Because think about a scale, right? I want to balance a scale. I want to give Tyrell this weight and the Lannisters the opposite weight. Okay? The rest of the groups will get 0 in this case. Okay? Not represented in this comparison. So, I'm just writing down these numbers. Okay? Now, I could have used 100 and -100. Doesn't matter. Okay? Will not make a difference. The only thing that matters is to correctly represent the comparison I'm interested in. Okay. Is this stage of assigning weights, that's what we call it, assigning weights or assigning contrasts. Is it clear? Okay. So, first of all, you see that if I summarize all the weights, they sum up to 0. That's very important, right? If I would use 2 and -1, that's not a valid comparison. Right? It's like giving the Tyrells 2 times the weight. So they have to sum up to 0. That's just the first rule. Now, how to check for orthogonality? The comparisons are orthogonal, independent, independent if, first of all, we multiply the weights assigned to the comparisons. What does that mean? Multiply the weights. C1 times C2. So this means that I'm going to multiply 1 by 0. Okay? I'm going to go 1 to the other, 1 to the other, 1 to the other. And then I'm going to this sigma. Sigma says summarize. Okay, sorry. First of all, so 1 to the other. Tyrrell's 1 times 0. Okay? Is it clear why C1 times C2 for the Tyrrell's is 1 times 0? Is it clear? 1 from the first comparison, 0 from the second comparison. I see doubtful eyes. Lannisters, -1 times 0. Okay. Baratheon, 0 times 1. Starks, 0 times -1. Targaryen, 0 times 0. First stage. Second stage, I summarize. These are called the products, right? This is the sum of products. Product is just the multiplication of the two numbers. Okay. I summarize all of these. And if the sum of the products equals to 0, we say that this is an orthogonal comparison. Okay, that was a bit intense. Okay, so the sum of C1, contrast or the weight applied to the first comparison, times C2, the contrast or the weights applied to the second comparison, if we summarize all of these multiplications, all of these products, we get a number. If this number is 0, we say the comparisons are orthogonal. Just a second, I'm going to show a case where it's not orthogonal. Okay, and see it. So this is C1, this is C2. Let's look at this comparison. Okay, comparison number 3. And now let's look at whether C1 is orthogonal to C3. Okay. So 1 times 0, minus 1 times 0, 0, 0, 0, 1, 0, minus 1. We got 0. Fine. That's good. But let's see if C3 is also orthogonal to C2. And then 0 times 0, right? You all following me? 0 times 0, 1 times 0, minus 1 times 1, and 0 times minus 1. Eventually, we don't get a 0. Okay? This means that this is not an orthogonal comparison. Just a sec. Comparison 2 is dependent on comparison 3. Okay? And we can see that the Starks fought against the Baratheons. We know that the next comparison has to be an alliance between the Starks and the Baratheons. Okay? They can't fight alone anymore. Just a sec. Okay? They can't fight alone. So every comparison where the Starks fight alone will not be formally orthogonal. Now the problem is that I need the entire set of comparisons to be orthogonal. So if C1 is orthogonal to C2, and C1 is orthogonal to C3, but C2 is not orthogonal to C3, the entire set of comparisons, this entire 3 comparisons, are not considered orthogonal comparisons. Again, just a sec. Comparisons 2 and 3 are not orthogonal. This means that the entire family of comparisons are not orthogonal, or the family is not orthogonal. Okay, so for a set of comparisons to be orthogonal, all the comparisons must be orthogonal to one another. Okay, we have a lot of questions, so let's go one by one. Yes.
Remember correctly, the way you, in the beginning, you said that you didn't define dependent like that. You said that if we know that, let's say,
Right, the informative intuition. Right? This doesn't seem very informative, this. Right? That's what you mean?
Yeah.
So, intuitively, that's what the intuition is not absolutely correct. Right? Because intuitively, I agree with you completely. But formally, this is not completely independent from one another.
But if you know the star is bigger than Targaryen and it's smaller than Baratheon, so we know Baratheon is bigger than Targaryen, so it is dependent.
Okay. There's some information that we can, yeah, I can see that.
What happens when you group them together?
If I group Starks and Baratheons,
It's a zero?
Yeah, so then they would come down to the next
Okay.
line, and then they
It's a
win.
zero?
wait. So let's give numbers, okay?
No, we leave
So-
the same numbers.
So let's apply numbers, okay? I'm going to write it down over here, okay? Let's do it together. So let's say we want Tyrells and Lannisters versus Stark and Baratheons, okay? So Tyrells will get, no,
Why would
Tyrells
they do it? They get one.
-1 and -1. Shh. Okay, Tyrells and Lannisters are together. So they're both on one side of the scale. And then Baratheon and Starks are together, both on the side of the scale. And then Targaryens will get 0. So, 0, let's see, comparison 2 versus comparison 3. 0 times -1, 0. 0 times -1, 0. 1 times 1, 1. Plus -1 times 1. So plus -1. So we get 0 times -1, and 0 times -1, and 1 times -1, and 1 times 1, and 0 times 0, plus equals 1 minus 1 equals 0. So again, this is formally orthogonal. Okay, we have more questions. Yes, want to ask? Answer. Okay. Okay, so this is just a second. This is important. Okay, we need the entire family of comparisons to be orthogonal to one another. This means that if I have 10 comparisons, I'm going to have to check all of them. Okay, 1 to 2, 2 to 3, 1 to 3, 1 to 4, 2 to 4, onward and onward. Of course, we are not interested. This is a rather easy process once you do it a few times. Okay, but we're not interested in you doing it in the test for half an hour. So of course, it's not going to be that big a deal. Yes,
Where did the numbers come
I invented them.
from? No, I mean not from this example. I mean when you're calculating. How do you solve to get the number?
I decide on the weights. We have just run one rule for the weights. They have to properly represent what we're looking for.
Yeah, so that's what I mean. Like, how do you decide or get the number?
I could decide if this was 100 and minus 100.
Why should
No, I understand that. I'm just saying, how do you know that one is the positive and one is the negative?
Ah,
Where-
doesn't matter. Doesn't matter.
What do you mean? doesn't
Why
matter?
doesn't it matter? That this is statistically
Why can't they
irrelevant.
both be one?
If they're both one, they're both on the same side of the scale, right?
Yeah.
And then it's not balanced.
Why would, I mean, what determines it has to be balanced?
So that's just,
I mean,
if you want, we can go into it like more intensively, but basically we're contrasting two comparisons, two averages. So if you want to contrast them, you have to make them on opposite sides of the scale.
But-
That's what makes them on the opposite sides,
so why not one? I mean, why, it's just arbitrary. Why not 1 and 2? I mean,
because then it won't be balanced. You'll see it in the
Right, but-
formula. Once we get into the formula, you see it makes a lot of sense. Yes, one more, and then we continue.
So they represent the average. That's all I'm asking. So
The
if the
way-
average is higher of 1, then you get a 1, and if it's
No.
lower than
No, you'll see it doesn't matter. In a sec, you'll see in the formula itself that giving it 1 versus -1 or -1 versus 1 won't matter.
But then what's the significance of this if I'm just making up arbitrary numbers? Like, what am I testing here?
You're just testing the contrast between them. The weight, that's all it
But
represents.
I'm making it up.
No,
Well,
you're
that's what I asked you. Where's the number coming from?
you're
You
looking-
made it up.
if you're interested, if you're looking at the Tyrrell versus Lannisters, that's your theoretical question, right? And then you're contrasting Tyrrell versus Lannister. Okay, that's the contrast you're looking for. So the weights just describe this contrast.
So your description is arbitrary.
Okay, so I'll ask you to come afterwards. Okay, so I have to continue. I think I understand what you mean, but I think I can convince you afterwards. Okay. Okay. So we can do the same process of formally looking for orthogonality in all the comparisons that we do. Okay. So in this case, we saw before that these intuitively were independent. I invite you to try this at home and look that all of them are independent. Practice. And you have the recitations to practice as well. Now I have a question. Do you think we can add another comparison? We had 4 comparisons so far. Can we add a 5th comparison which will be orthogonal? I'll give you a dare. Try this at home. If someone finds a 5th comparison that's orthogonal to all the other comparisons, you get 5 points in your group. Okay, 10 points in your group. Okay? Because
This is your question.
this comparison 5 in this case can never be orthogonal. Okay? Absolutely. You shouldn't try. But the point is that, well, first of all, it's good practice, right? It's good to see that whatever you try, it won't work. Okay?
But all 5 against successive revolution.
Again, we had one of the students in Tel Aviv said that Chuck Norris could find a 5th comparison, which will be orthogonal. So the rule here is, and it comes from the formal way of checking for orthogonality. Okay, it's not like a mystic rule. It's just you won't find anything else. A family of orthogonal comparisons can only include up to, right? I could have done only 2 comparisons or 3 comparisons, but up to k minus 1 comparisons. Okay. I can never have more than k minus 1 orthogonal comparisons. So any other comparison you add here will necessarily be not orthogonal to at least one of the comparisons. Okay? A family, right? We said that this is a family of comparisons. A family of k minus 1 orthogonal, right? I forgot to say orthogonal comparisons, is called a full set. It's a full set of comparisons. Okay? So you don't have to conduct a full set of orthogonal comparisons, but that's the maximum you're allowed to do. In this case, in my study, okay, I had 4 groups. I did only 2 comparisons. I could have done 1 more. Intuitively, who can see what other comparison it could do? Heterosexuals versus gay, right? Because they have an alliance, and I can break down the alliance. But I just chose not to. I could have, without inflating the alpha. It was just not of interest to me. Not part of the study.
Why will you do it? Find why.
I could find if there is a difference between the evaluation of heterosexuals and gays. I could have. If you want, I invite you all to read the study, Zivoni and Nobel 2014. By now, you have a lot of the tools to understand, I think, 99% of the analyses. Okay. Any questions about this idea. Okay. Yes. Or father.
Yeah,
Independent if you don't want to say
yeah,
that.
independent, so, but that doesn't give you that much about. Because K minus one gives the amount of groups, right?
Right.
So if I have 4 groups,
You can have up to 3 comparisons.
yeah, so they're not all independent.
It depends on this, right? If they
You're
are
just saying there's no possibility that it's
Right.
K minus one.
the maximum is k minus 1.
So the maximum is K minus one, so it's gonna be one comparison that's not independent.
If you do 4 comparisons, right? If you do 3 comparisons, right? In this case, we have 5 groups, right? We have 5 groups.
As the amount of comparisons you choose to take out of the group.
Yeah. Yes.
What kind of test are you running within the comparisons?
You mean this? What is this called?
Within the comparisons, when you're running, like, for example, Tyrell versus Leinster, what kind of statistical test are you running there?
Next slide. Good. So far we talked about planned comparisons. Now I'm going to show you how do we conduct a planned comparison. Okay? First of all, this makes sense. Each comparison is tested separately. Okay? Guys, it's not, I don't have the microphone, so I need you to be with me. Each comparison is tested separately, meaning, of course, if I want to do the first comparison, I will conduct a separate statistical test from the second and the third and the fourth comparisons, right? So each line is a separate statistical test. And of course, I have, in this case, 4 conclusions. Okay? I'll have a conclusion about each one of the tests. After we place the weights, we use the following formula. So this is the first step. This is called SS comparison. SS comparison, basically, it's the sum of squares between the groups for the specific comparison. Okay? SS comparison, SSB for the specific comparison. Sometimes you'll see it as SSB comparison, sometimes you'll see another way of defining it. It doesn't matter really the name, we just have to understand what it means. So, as usual, a formula full of letters which is not really comprehensible. Okay? So let's go over it slowly and understand it's not that big of a deal. So, what do we have? This small part is the number of subjects per group. Okay? This W is the weights. Okay? And this X bar is the group average. So what do? In the numerator, we sum the squaring of the weight times the average. Weight times the average. Okay? And in the denominator, we sum the weight squared divided by the number of subjects. Okay? So what will that give us in this case? Okay, so we have, this is the comparison we're conducting right now. We're conducting Targaryens, right? Targaryen will get -4 versus 1, 1, 1, 1. Okay, everybody with me? Comparing Targaryens to all the rest. Yes?
Weights are absolutely arbitrary. You assign them based on.
I
whatever-
assign them. It has to be 0. 1 plus 1 plus 1 plus 1 -4. It has to be
No, I understand that. I'm just saying that which one you decide is going to be the positive or the negative, that's
Right.
an arbitrary.
absolutely.
The
And why it won't matter in a second. So let me show you the result, okay, before we ask any questions. We get this long thing. Everybody, please be with me. Okay, weight times average. So 1 times 6, right? Average for Tyrrell's is 6 times 1. Plus, we're summarizing. 1 times 10 plus 1 times 8 plus 1 plus, times 12 plus minus 4, right? Minus 4 times 14. Now, what do we get eventually? We get a number representing the alliance of Tyrrell's, Lannisters, Baratheon, and Starks, the sum of all of them together, minus a number that represents the Targaryens. And we get this gap of 20 points squared. Why doesn't it matter if these are 1 and this is minus 4 or vice versa? Because we're squaring it. It could have been, this is minus 20. It could have been 20. Minus 20 squared, 20 squared, doesn't matter. Okay. Divided by the sum of 1 squared divided by 20. 1 squared divided by 20. 1 squared, minus 4 squared divided by 20. So in this case, it fits neatly. We get divided by 20 divided by 20. So 20 squared is 400, divided by 1, we get 400. Okay. So this process will give us the SSB for the comparison. Right? This is the obtained difference for this comparison. Okay, now you can ask questions. Yeah.
I'm having a hard time. When we're making all of them one, another one negative 4, I know it's because we're trying to get a balance.
Yeah.
But I feel like that's making the Targaryens have just as much strength as all 4 of them together. They might not be that strong to giving.
Good. So far, I've been I made a small logical gap. Okay? Logical step. I don't know what to say. So far, I implied as though I'm asking what would happen if all of these houses together will march against the Targaryens. But that's not exactly what we're asking. It just seems like that because we're talking about Game of Thrones.
Right.
What we're asking about really here is whether the average fighter from 4 of these houses will win against the average fighter again of the Targaryens.
But why would the average of their 4 be equal to the average of just the 1? As in, that
Because
balance is happening, but why? Like, what if their 4 averages are actually way stronger than the Targaryens? Yet they make
Then we'll see that.
We'll see
If
that.
the entire 4 averages, we'll see that it happens exactly that. Another way, if you think, if you want to go into the formula, you can. But basically, if you take these 4 houses and just decide, okay, I don't have 4 houses, now I have only 1 house with 80 participants, okay? And you would give this average, right, the average of all the houses and 80 participants, and then conduct the t-test, you'll get the same result, okay? You'll get exactly the same. So basically, what we're doing here, right, it's not the sum of all of these, it's the average of all of these. And this formula will give it the appropriate weights to be the average. Yes?
What about the direction of the relationship?
So again, because we don't directionally
know.
mean 1 or minus
It's
1.
bigger, we don't know.
Right, we don't know and we don't care. Because we're squaring it. Because of this squared, we don't care if it's negative or positive. Yes?
So it only worked out nicely on the denominator because we had the same amount of people in each group.
Yeah, otherwise you have to calculate it more. It would have been a bit
When
more
there's the same
difficult.
amount of people in each group, it's always going to be 1. When there's the same amount of people in each group, it's always going to be 1.
No, not at all. Not at all. You can see in other comparisons, if you'd have 1 and minus 1, you would get 2 divided by 20. It's just by chance because of this was 16. You got 20 divided by 20. Every time you have to look at it, there's no rule to it. Okay, so this is the formula. Okay, this is the first step of conducting our comparison. Okay, we're summarizing this difference between the groups divided by this weight.
What is the significance of the denominator?
What does it mean?
So I'll just say, think about it this way. When we calculate SSV, we multiply by the number of people, right, in each group. Here, in the denominator, we're dividing by the number of people. So if you reverse it, you'll see that we're multiplying this number. Okay? So we're doing exactly the same process. Exactly. Okay, but that's not important. Okay, next step. So we have SS, another way of writing it, okay? SSV of 1 plus 2 plus 3 plus 4 versus 5, okay? So another way of writing it. SS comparison, SSV, same thing. Now, MSV is SSV divided by K minus 1. Now, in the original
So it's 1.
Omnibus ANOVA, K was 5. So intuitively, we want to say, okay, K is still 5, so K minus 1 is 4. But I told you this comparison is like a scale, right? We have Targaryens versus a combination of all the rest. So essentially, we have two groups. Exactly.
So it's always 1.
Always one. Whenever we do a planned comparison, in planned comparison, the degrees of freedom between is always 1. Because we're always comparing essentially two sides or two groups. One group could be comprised out of 4 groups, 5 groups, 10 groups. But eventually, the degrees of freedom between is always 1.
So SSP is always MSP.
Exactly. Don't worry, you'll have a lot of time to practice it in the presentations. MSW equals to this. Sorry. SSW divided by Okay, sorry, I jumped ahead. Okay. So this is a small theoretical point. I'm sorry, I think it's a bit heavy already, but bear with me. What is the MSW? Okay. We could have calculated a new MSW for each comparison. But according to the assumption of equal variances, the variance is equal for all the different populations. Right? We assume that the variance for the Targaryens is the same for all the different houses. Okay? Accordingly, MSW should be roughly the same whether we use SS from one group or all the groups. But the more participants we have, the closer we are to the population. The more participants we have, MSW becomes a better representation of the population. Okay? Is that clear? Right? We sample more people, we get a better estimate of the variance in the population. Therefore, in between subject analysis, we will always use the error factor that is pulled from all the available groups. Okay? Even if I'm comparing now only the Starks versus the Baratheons, I will still use the MSW from the overall ANOVA. Okay? The reason is not because MSW is smaller in the overall ANOVA, it's simply because it's more accurate. Okay? More participants, meaning that we're closer to the actual estimate of the variance in the population.
Assuming that it's one population.
We always assume.
It's not about whether it's the same population, it's about the amount of variance within each population. Even if they're different populations, we're assuming that the variance is the same in all the populations. Right? So, when we're asking what is MSW, I'm going to the next slide. Sorry. As a bonus, we get more degrees of freedom. We'll see that in a second. MSW is the same MSW we calculated before. Same SSW, same degrees of freedom, right? In plan comparisons, SSW and DFW equal the SSW and DFW from the ANOVA. And I have two advantages. One is that MSW is more accurate. Two, that I get more degrees of freedom. Whew, long process, right? One more step. Only if it's important because we have to move on. If any other theoretical questions, come after the class. I really like it that you're interested, but still. Last stop is the F for the comparison. MSB for the comparison divided by MSW from the entire design, right, from the omnibus ANOVA, we get F equals 16. We compare it, of course, to a critical F. Which critical F? Critical F with 1 degree of freedom between, right, and 95 degrees of freedom within. Yes?
But although I saw the numbers, group 2 is bigger, we still don't have the relationship in the static calculation.
What do you mean the relationship?
The group, they're different, the groups are different. They don't say which one is bigger.
Right, but that we can see in our eyes.
Yeah.
We can see in our eyes that the average for the Tigerians is larger than the average for the rest.
Yeah.
So that's fine. That's in the details.
That's enough.
So F for the comparison is larger from the critical F, okay? Which means that we have a significant result. Meaning in this case that the Targaryens are better fighters, will win in the fight against the average of all these 4 houses. P is smaller than 0.05. Targaryens are better, like this. That's the process, okay? That's how we conduct plan comparisons. Any questions about this process? Let me summarize it. We give weights to the comparisons. We look if the weights are orthogonal to one another. We saw that they are orthogonal to one another. Then we're looking at one comparison at a time, and using the same weights that we've chosen for them, we're using the formula for SS comparison. And eventually, we compare the obtained difference to the difference expected by chance in the sample. Okay? And the F will represent that, comparing to the critical F, and then concluding about the comparison. Of course, we'll do this process for each comparison. Okay. And in this case, we have 4 conclusions. Specifically, we see that comparison 3 was not significant. Okay? A lot of work. I've promised you and I promise you again, in the test, you won't have to do all this work. Maybe in the homework, you'll have to do it once. Okay? But in the test, there's not a lot of algebraic work. 1 or 2 more things. Okay? Then we're finished with it. I want to show you something neat about independence. Okay, this is something, A, it's important, B, it's going to be in the quiz, C, the TAs won't cover it. Okay? So this is important. In the ANOVA, right, the overall ANOVA, the omnibus ANOVA, SSB was 800, right? In our full set of orthogonal comparisons, right, I showed you this, we just skimmed over it. But for every comparison, I have a separate SSB, right? SSB for 1, SSB for 2, SSB for 3. In a full set of orthogonal comparisons, what do we see? 160 plus 160 plus 80 plus 400 will equal to SSB from the overall ANOVA to this. Okay? So here's a neat rule. Whenever we conduct a full set, right, k minus 1 orthogonal comparisons, the SSBs from the comparisons will summarize to SSB from the overall ANOVA. Why is that? I'll show you the text in a second. Think of between group variance as a piece of a pie. Okay? And when you're conducting plane comparisons, you're cutting pieces of the pie. Now, when these comparisons are independent, you're cutting up different pieces of the pie each time. Okay? You're cutting it up neatly. There is no overlap between the variance that you analyze. Right? So a plane comparison uses a part of the between group variance. The orthogonal comparisons do not overlap, meaning they use different parts of the variance. A full set of plane comparisons uses all the between group variance. The ANOVA asks something about all the groups in combined, how different are they? And the plane comparisons ask specific questions about specific groups. Okay? So it uses the same kind of between group variance, and when we have a full set of plane comparisons, it uses up all of the variance neatly. Okay? No overlap. Non-orthogonal comparisons use the same variance in more than one comparison. So another way to imagine, it's a bit imaginary. We have to imagine this pie. Okay? When we do two comparisons which are non-orthogonal, we use the same variance twice. Okay? So not being independent means that I used up the same variance twice. It's not using up, not spending it away. You do the same comparison again. Okay, so this is the main rule to remember from here. Okay? That in a full set of plane comparisons, then we know that SSB from all the comparisons will sum up to an SSB from the overall ANOVA. From this small rule, we can do a lot of small mathematical games. Okay? So for example, if I know, let's say from my study, okay, if I know that SSB from the overall ANOVA was 1,000, and SSB from the, sorry, I can't read here. Okay, SSB from this was 600, and SSB from this was 200, okay? Now, if I compare the gay group to the heterosexual group, what will be SSB? Not 0, 200. Let me do the process again, those of you who missed it. Okay, I have two orthogonal comparisons. If you get this, this is the integration of the entire class. Okay, we have two orthogonal comparisons. I can add one more orthogonal comparison. We said before, it's the heterosexuals versus the gay group. Okay? If I have a full set of plane comparisons, comparisons, their SSBs will summarize to the overall ANOVA. So 200, 600, the last comparison has to be 200. Okay? Has to be 200. Okay, so this is a nice game to play around with numbers. You'll see it always comes up to that. Okay? If you don't trust me, try it yourselves, do it a few numbers. I know, trust me. Okay, long lesson today, right? A lot of new material. I think one more slide.
No, it's the salad one.
That's the last one. That's the last one. Last one. And this is to answer your question before. Okay? So, plan comparisons instead of ANOVA. I just said that a full set of plan comparisons uses up the same variance as the overall ANOVA. And I'm telling you, it's not good to use up the same variance. But if I do both the ANOVA and the orthogonal comparisons, I used up the same variance exactly twice. That's why, actually, we don't even have to do the ANOVA. Okay? In actual research, if we have planned comparisons, there's no reason to go into the ANOVA, because you know what comparisons you want to do. That's a statistical rule. However, the norm in studies will be, okay, you want to do planned comparisons, please show us the ANOVA first. But don't worry, if you have significant planned comparisons, most chances are you'll have a significant ANOVA as well. So it's not true that you have to do both the ANOVA and planned comparisons, but most journals will ask you for both. That's it. Thank you very much.